Now for this video, we're going to use the insurance data set, and we are going to apply the principal components and tSNE analysis to it. So let's get started. So because we're going to be using tSNE, we got to load in that library, and we're of course going to need our random forest for later on. So let's load those guys in, and let us also load in our data set. So what do we have? We got this guy, and if we do a quick look at the data frame, you can see this is the data frame we've been working with all quarter long. This is our, did the person crash their car? How much did we spend to fix the car? We've got all of our variables. They have been, we don't have any missing values. All of our categorical variables have been converted into flags. We're good to go. So, and of course you can do a summary and the structure of the data if you really want to do that too, but we don't need to do that, but the code is there. So what we're going to want to do is first get rid of your target variables. So if you're falling asleep, wake up. This is very important. If we're going to do our principal component analysis, you do not want your target variables in the principal component analysis. So let's get those guys away. And if I do, look at that, we don't have our target variables now. Okay, great. Now the next question is, should we use, look, there's 45 variables here. We're going to use all of them? Well, I'm not a fan of putting flag variables, ones and zeros. I don't like to put those into principal components. They tend to either overpower or they underpower. In other words, they either overperform or underperform. They can either massively affect your principal components or have no effect at all. So they don't ever do the right amount of work. So I don't like them myself. You can try them and see if they work for you. But I'm going to try them briefly and then I'm going to move along. But let's just do that. I'm going to use this guy here, principal component, and I'm going to use all of the variables. I'm going to center it and I'm going to scale it. So we're going to do those standardization. Let's do that, and we can do a quick summary of this. So we do the principal component, and here's our summary. And you can see here that we've got 45 principal components. We're not going to want to use all of those. We can say, well, how many variables should we use? Well, let's take a quick look. I would say let's first do a scree plot of this and see what we get. And when we do a scree plot, we can say, oh, it comes down here and sort of flattens off around 5 or 6. We could maybe use 6 principal components. If you want to also look to see where the variance is less than 1, well, you would have to look at the summary. And if you look at the standard deviation, you can get an idea. Well, you say, well, wait a minute, that's 2 and this guy is 5 plus. Well, that's because this is variance and this is standard deviation. Well, if you square this guy, you're going to get this guy. So we can just, either we can do it by hand and we can calculate it, or you can just still look for things that are less than 1. And if we go forward, we find around principal component number 19, this is where it goes less than 1. So we could say that it flattens off around 5 or 6, and we can go as far as 19. I wouldn't go that far, but you could. I would personally, if I was going to look for things that are, more than 1, maybe I would stop at 7. So it seems to flatten off around 7, and maybe the variable, the principal components stop being useful around 7. 7 might be a good number. I'm not going to use 7 right now. I'm just going to use 2 for this purpose. Well, what do I do now? I'm going to take and I'm going to predict. So I'm going to say principal component. That's my model right here. And I'm going to predict my principal component guy right here. I'm going to predict him, and I'm going to shove the answers into df new. and df new, oh, let's do a head command here, head df new. Okay, and you see I've got each of the rows has 45 principal components, and we can use as many as, let's say, 7 of them. I'm not going to use all 7 right now. I'm only going to use 2 for right now. And so I'm going to take and copy data frame into here, and I'm going to copy the first 2 principal components into here. Now the reason why I'm using data frame is I want my targets back now. So let's go grab the original data, tack on a couple of principal components, and let's see what we can do with that. So data frame, so if I do head, data frame, and I'm calling this flags because I'm using the flag variable here. And you can see I've got the original data, I've got my targets, got all the original data, plus I got these 2 principal components. So now I'm about to run this code, and let me delete that line. So this code from here to here, I'm about to run this code, but it's not going to do anything because this line right here undoes it. I'll explain what this code is doing in just a moment, but let's take a quick look at this guy right here. So let's run this code. And now let's graph our principal components. And we're going to color it by whether or not you crashed your car. And you can see here that it kind of looks like the right side of the screen has more black dots. The black dots are the people who crashed their car. So this might be a predictive variable and might be useful. I'd kind of like to clean this up a little bit and see if we can see anything. So let's take a look. How might we do that? Well, let me uncomment this thing, and I'm going to show you what I did. The first thing is, what is this code doing? This code is going to take a random sample of my data so that I can see a less dense graph. So the first thing I'm going to do is create a random number from 1 to 100. And I'm going to call it random 1 and random 2. Let's take a quick look at both of those. And if I do head of data frame flags, you can see that I have my principal components, and now I've got these 2 random numbers. Now I'm going to copy all of the guys who are zeros. They didn't crash their car, and they're going to go into this variable flag 0, and all the guys who did crash their car are going into flags 1. So let's execute that code. And if I do a dimension of df flags 0, we've got 7,500 people who didn't crash their car, and 2,700 people did crash their car. Now you'll notice that I haven't really created a holdout sample, and I probably should do that, but for this purpose I don't care. I'm just trying, this is all for demonstration purposes. I'm probably not going to use any principal component analysis for this problem. I just want you to be aware of what a principal component analysis is used for and how it might be used in a real world situation. But here we go. You can see that I've got a lot more people who are driving safely than risky drivers. So I'd kind of like to even that out a little bit. So how might I do that? Well, what I'm going to do is I'm going to take a smaller, 25%, about 1/4 of these people, because I'm going to say my random numbers from 1 to 100. So give me about 1/4 of those into flag 0, and give me about 3/4 of these guys. So hopefully this will even that out a little bit. Let's try. So now if I do a dimension of flag 0, I've got 2,500 of those guys, and let's see how many I've got of flags 1. I've got, flags 1, I have 75. How did I get 7,500 of those guys? 7,700. dimension flags 1. Oh, I see. That's my mistake. I should have done flags 0, flags 1. Let's try this one more time, shall we? Okay, now let's try it. I forgot to put the 0 and the 1 there. So let's see what the dimensions are now. So if I do dimension of flags 0, I've got, whoops. Oh, let's spell it correctly. DF flag 0, I got 1,700 of those guys, and flag 1, I've got 1,900. Okay, great. I've got about the same size of both of them. Okay, let's put them back together again. So I'm going to merge both of these guys back together. I'm going to do a row bind, and I'm going to put in the 0s over here and the 1s. So I'm going to merge them into one data set that I'm calling flags X. And let's do a dimension of this now. Dimension of flags, DF flags X. And I've got 3,700 of these things. I'd like to get that to be a smaller number. So let's take about maybe, oh, I don't know, 15% of them. Let's try that. So DS flag 0, DS flag X, there we go. And now so this is what it looks like now. Let's take a random sample and see if we can get a better picture of this. And you can see that a lot more of the black dots are over here on the right side. So I don't know, maybe if I were just eyeballing this, I would say, yeah, these are predictive. Looks like principal component 1 is real predictive because the higher up you get, the more black dots you get. Probably this guy doesn't seem to be all that predictive, this vertical guy. But anyways, this is how that is done. I mean, so this is where we used all of the variables, all 45, and we probably could get by with just using one principal component. It looks like this guy's pretty predictive of whether or not you crash your car. But like I said, I'm probably not going to use this guy because I don't like to put flag variables into my principal components. My personal choice. I'm not saying you can't. I'm just saying I don't recommend it. So instead, I'm going to do principal component 2. I'm going to call this PCA 2. And this one's just going to use these guys right here. Variables 1, 2, 3, 4, all these guys here. And these are, if you look at that, let's go over here and let's do a head command of dfPCA. You'll notice that these guys are the variables that are not flags. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, don't want 11, so I go 10, 12, 14, 16, 18, and that's it. So let's see which ones I'm using. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, 18. I'm using only the numbers, not the flags. So let's do that. And let's do a quick summary of that. And there we go. Now we've got 14 variables. 1, 2, so we've got this many principal components. Now the neat thing about this is now that we have like 10 variables or 14 variables here, it's going to be a lot easier for us to actually tell a story on this data. When you got too many variables, it's hard to tell a story. So let's tell a story. Let's type PCA 2. Well, let's first of all see how many how many principal components we want. So let's do a scree plot and see what we're going to do. And I'm looking at this, and I think I might go 1, 2, 3, maybe 4. I'm going to take the first 4. Okay, then it really flattens off. I'm going to do the first 4 of these guys. And, you know, you might even say I'm taking the first 3. We could do that. Let's just, we'll take it at the first 3, or the first 4. So let us see what the first 4 look like. So I'm going to type principal component analysis 2, and it's going to give me all the principal components. Now, if I look at this, let's do that again. I mean, let's tell a story with this data. What I do is you look at the principal component, and then you look at like the biggest number, and the biggest number, whether it's positive or negative, you just look for the biggest number. And it looks like for principal component 1, the biggest numbers are negative. That's okay. It doesn't matter. It's just what side of the axis you're on. But it looks to me like I've got big numbers for home value, big numbers for income, big numbers for your car, big numbers for your age, but that may or the blue book value of your car. So what this is telling me is that these are kind of variables that are associated with wealth. So the bigger the negative number that you have, the more money you got, because these are negative numbers. What about so I'm going to call principal component 1 wealth. It's not perfect, but if you had to tell a story, you'd say this is wealth. What about this guy here, principal component 2? What would I do? I might say that, oh, look at this. Oldest claims. Did you crash your car a lot in the past? And it's a big negative number. Okay. Claim frequency. How much did I spend in the past to fix your car? How many times did you crash your car in the past? How many traffic tickets do you have? And then I would call this like risky behavior. So if you've got really high negative numbers, you're risky. What about here? Principal component 3. It looks like the big numbers here are positive. Kids drive home kids. This is like, are there kids at your house? Big positive numbers mean you got kids. Kids are not your friend when you're doing auto insurance because children crash the car more than adults. What about number 4? What do we got here? This is a big number right there. And that one is time in force. This is how long have you had your policy, your insurance policy. When you have an insurance policy a long time with an insurance carrier, that usually means you're safe. Why? Because if you don't, it means that you, usually if you have a couple of major accidents, the insurance carrier drops you. So if you've been there a long time, it means you've been safe for a long time. Okay, so these are my first 4: wealth, risky behavior, kids, and history of being safe. Okay, let's take a look at that. Let's copy this, and this will be our principal component analysis, no flag variables. And let's, did I score them already? I think I did. Let's do it anyway. Let's score it and take the first 4 variables. So let's see, DF or head, DF, new. Yeah, I got all 14 there. And if I do head of data frame, no flags. Okay, there we go. We've got all of our data, and here they are, our 4 principal components. So let us come down here and let's do a quick visualization of principal component 1 and principal component 2. And let's see if we can see any patterns. And again, remember, a high negative number means that you're rich. Well, it looks like, well, maybe I'm wrong. Maybe it's just the opposite. I don't know, but you see that um, large values for principal component 1 seems to have a lot of black dots. They crashed their car. Also, people at the top of principal component 2, there's a lot of red up there. It means that they didn't crash their car. But it's kind of hard to see. But this looks like it's somewhat predictive. Let's take a look at some of the other ones. Let's look at 1 and 3 together. And we could do 2 and 3. We could do anything we want, but I'm just going to do everything with 1. Okay, there we go. Again, principal component 1 seems to be predictive. Oh yeah, well, yeah, wait a minute. A low principal component 1 means you're rich. Okay, so rich people are down here, poor people are up here, and the poor people crash their car. That makes sense because the wealthier people tend to not drive as much. You know, when you're in the car, it's when you crash it. Let's see if we do anything else. And again, this is principal component 4. Now, what we'll do is just for fun, let's get rid of this. We'll take a random sample. And let's run this particular one. Let's run this last guy again, and we'll see that it's going to be a lot less cluttered. And yeah, that doesn't look all that predictive. It looks like that those black dots are evenly distributed everywhere. What about the first guy? Maybe up here at the top there's a lot of red. So maybe this is predictive, and a high value for principal component 2 seems to be safe. So maybe principal component 2. Well, what was principal component 2? Let's take a look. PCA 2. Principal component 2 was oldest claims, speeding, and so if you have a negative value, it means that you crashed your car a lot in the past and you speed a lot. So high values means you're safe. Okay, well, that makes sense. So principal component 2 seems to be really nicely predictive of whether or not you're going to crash your car. And we could do the same thing over here with this guy. So this one doesn't look all, it looks like it's all scattered around. So we could, you know, play around with this stuff and see what we could find. But now we're going to explore. So, I mean, I might use these guys, 1, 2, 3, and 4 in a model, see what comes out. But instead, let's move a little bit further and let's do tSNE analysis. So we're going to start off with 30 as our perplexity, and we're going to use, in this case, I'm going to just take and copy all of the data. And then remember, we have to use the unique command, or let's get rid of the amount, because we're only going to look at the flags. Let's use the unique command, and then we'll do the head command to see what we got. Okay, there we go. And we got this target guy, but we're not going to use him in our tSNE analysis. You don't use your targets in your principal components. You don't use your targets in your tSNEs. I'm only going to use the numbers. That would be, this is 1. We're not using 1. We're going to use 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, not 14. We're going to use 15. We're going to use 17, and we're going to use 19. Okay, so let's see what we got. That's what we have right here. So we're going to use the tSNE. We're going to go for 2 dimensions, and we're going to go for a perplexity of 30. And then we're going to do a quick visualization of that. Whoops. and this takes a little bit of time to run. And the first time I'm going to run it, and then I'm going to pause it for going forward. So we wait for this to run, and we'll see what kind of perplexity we get, or what kind of graph. Wow, that looks kind of cool. Do I see any patterns here? Not really. I mean, it looks like this guy down here seems to be got a lot of black dots, and over here, this red guy in the middle. And okay, but remember what I said before, you're gonna want to run this a bunch of times, because if I run this again, let's run this guy here a second time. Now I'm going to pause until this stops running because I don't want to waste a lot of time. And we're back. So now it's got a new one. Let's graph it and see what we get. So again, this is a perplexity of 30. And that's a good starting off point. Everybody says start with 30. And there we go. We just got this guy now. Different shape. So I don't see any obvious patterns in here. So let's change the perplexity. Let's go down to a number like 5. Okay. And let's run that and see what we get. So let's go here. And we'll pause. And we're back. So now let's do a quick graph of this guy. And you notice it's less dense because I had a perplexity of 5. So it kind of looks like maybe a little predictive. It looks like most of the black guys are on in this little bubble here, but it's not. I don't like using 5 in this case. It just looks like there's no obvious clumps of data. Let's clump it up a lot more. Let's take that guy up to 100. Okay, so let's run this guy and see what we get. And I'm going to pause again. So now that it's back, let's run this and see what we get. So this is going to be hopefully more tight clusters. Let's see. Wow, that's actually really interesting to look at. It kind of looks like this guy here has a lot more black dots. It's a lot more dense. Let's try a few more and let's see what we can do. And I'll run the whole thing and then pause. And by the time we get back, this will change magically. Well, that looks interesting. Again, we got a big clump over here. Seems to be the dangerous ones. I find these interesting to look, very artistic. But I suppose that's neither here nor there. We'll go with this one right for this. Let's move along. And because we cannot score using, there's no predict command for tSNE. Remember how we have a predict command for principal component analysis. Where are they? Right here, we have a predict command. We don't have one of those for tSNE. So what we need to do is use either linear models or a machine learning thing like a random forest. So let's go and build. First, we need formulas. Let's do those formulas. And if I do F1, you can see there's my formula. TS1 is going to be a function of all these guys, and formula 2 is all these guys. Okay, so let's come over here and let's build the linear models. And let's also come over here and build our random forest. Now, our random forests are going to take a while to run, maybe a couple of minutes. And that's going to be some dead air time here. So I'm going to pause until both of the random forests have finished executing. Okay, we're back, and we've got our random forest and our linear regression models are done. So let's go over here. Let's copy our data frame into this guy. and let us create TS1M for the model, TS2M for the model, and then TS1M random forest for a model and random forest 2. So let's get all of those guys and add them to the mix. Whoops. Okay, let's add those guys to the mix here, and there they are. So now if I do a head command of data frame tSNE, you can see I now have the linear regression guy and we have the random forest, and these are the approximations of this guy right here. So let's do a visualization, and of course right here this is the same command that's going to make it a smaller segment. Well, let's use all of it for right now. So let's use all of it, and let's first look at the linear regression. What kind of an approximation will it give us? Now, this is what tSNE is giving us. Let's see if we use linear regression to approximate it, how closely that looks. Doesn't do a good job at all. So I am not a big fan of using linear regression for approximating this stuff, something highly nonlinear. Just for fun, let's see how the random forest did. So this is, let's go back to what it looked like. This is what the original one looked like. And let's see what the random forest looks like. You know what? That's not, it looks like a duck. There it is, a little eye there. So this looks to me, my recommendation is for highly complicated, complex tSNE models, I would be using random forest or gradient boosting or something like that to approximate. It doesn't look like linear regression does a very good job of that. But anyways, it does again look like the guys over here in this clump seem to be highly risky, and maybe over here, you know, inside of this little loop seems to be risky. Real safe in this area. It doesn't look like there's a lot of black dots. We could see if we can visualize it a little better. Let's comment out this, and let's see if we can make, let's do this. And let's look at our random forest model. That's the only one we really care about. And again, look, this is almost completely black dots. This is highly predictive, very interesting. Okay, so, well, just to be complete, let's look at the linear regression one. See if that's actually, it might, even though it's not a good approximation, it might be useful. Look at that big clump of, yeah, looks to me like it's all, I can't see any big clumps of black or red. I mean, wherever it's black, it's also red. So it doesn't look like this is a particularly useful way of segmenting the data. At least not with linear regression. It looks like the random forest is a very much better. Anyways, so this is using real world real world data, and you can see that we have the tSNE and we also have the principal component analysis.